Today we're going to talk about a new type of integration that follows from u substitution, and it's when you have more than one trig function. Generally, you could have just one, but u substitution does not work. The first thing that sometimes we need to use are Pythagorean identities, and you learned those in pre-calculus. Sine squared plus cosine squared is 1, tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared. And by manipulating those around, you can make useful substitutions. For instance, if I solve for sine squared x, that would be 1 minus cosine squared x. Or if I solved for cotangent squared x, that would be cosecant squared x minus 1, for instance. So using those substitutions can allow us to make problems easier, to manipulate and integrate. All right, today we're just going to talk about the rules for sine and cosine. And you have three cases. You have even and odd powers, you have odd powers, and even powers. So when you have even and odd powers, that means one trig function is an even power or exponent and the other one has an odd power. And in this case, you break the odd power into an even power times a single power, and this single power serves as your du. And then you change the even power to be in terms of the other trig function using your Pythagorean identities. So that's what the directions say. Lots of words, so here's what I'm talking about. Cosine is cubed, so that's my odd power. So I'm going to break cosine down into, I'm going to leave the sine squared there. I'm going to break cosine down into cosine squared x times cosine x dx. Now, that means that my du has to be cosine. So if du is cosine, then that must mean my u has to be the other trig function, sine. Notice I'm not letting u be a power of sine, it's just regular sine, because du wants to be just the regular cosine with no powers. If I had a power on sine, I would have to use the chain rule, and that's going to give me more than one trig function for my answer. Okay, so if I want u to be sine x, I still have this cosine squared x. Well, I know that cosine squared x, from my Pythagorean identities, would be 1 minus sine squared x. So that means I can rewrite this problem as sine squared x times 1 minus sine squared x times cosine x dx. So now, when I look at my u substitution over here, I can say, all right, well that's just u squared times 1 minus u squared du, and I forgot my dx on my du. So everything is represented by u's that is over here in my integral. Well, in order to integrate this, I have to do some algebra. I need to distribute. So that would be u squared minus u to the fourth, all integrated with respect to u. And so that just means I add 1 to the exponent, divide by the new exponent in both cases. So u to the third over 3 and u to the fifth over 5. Don't forget to cupcake. So back over here to my problem. Don't forget to do that step. Coming back over to my problem, that means then that I have to change my u's back to what they represent. So this integral of sine squared cosine cubed would turn out to be sine cubed x over 3 minus sine to the fifth x over 5 plus c. And that would be the answer to my integral problem. So again, if you have even and odd powers, the odd breaks down into an even times an odd. That odd is your u. Excuse me, that odd is your du. That odd is your du. Okay? Second case scenario is if you have odd powers for both trig functions. Then you can choose which trig function you want to change. So if I have both cosine cubed and sine cubed, I can decide, do I want to change cosine or do I want to change sine? Well, since our du last time was cosine, let's make our du this time be sine. So that means that I want a single power of sine. So I'm going to break this down into cosine cubed x times sine squared x times sine x dx. The single power is my du, so I know du is sine x dx. And that would mean that u is cosine x. Well, there's a little bit of an issue here, because if I have u be cosine x, du would be negative sine x, right? So I'll have to deal with that when I do my integral, but no big deal. All right, so back over here to the problem, I have cosine cubed. That's okay. So I can keep that cosine cubed x. Sine squared x, though, has to change to cosine. So sine squared is 1 minus cosine squared x, and then times my sine x dx. So now I can represent everything with u's that I have over here on the left. So I would have the integral of u cubed times 1 minus u squared du. And because of that negative, when I write that problem out, that's an extra negative, so I need a negative out in front. So that would then, by doing some algebra, mean that I would have negative u cubed plus u to the fifth, it's the integral, sorry, du. So I distributed the negative. You could keep the negative out in front till the end if you wanted. I just thought it would be easier to get rid of it right now. So when I integrate that, that becomes negative u to the fourth over 4 plus u to the sixth over 6 plus c. So coming back over to my original problem, because u is cosine, I have negative cosine to the fourth x over 4 plus cosine to the sixth x over 6. Don't forget the cupcake. Okay? Hopefully that makes sense and is not too bad. So that's odd powers. All right, the tough one is if you have two even powers. Well, you really can't integrate with two even powers, so you have to use your double angle trig identities that you learned in pre-calculus and probably have not used since then, quite honestly. So if I look at this double angle for sine, it's sine 2x is 2 sine x cosine x. That really doesn't help me because I have a double angle here, but these are just powers of sine and cosine, all single powers, which really doesn't help me. But if I look at the cosine 2x, that is in terms of cosine squared and sine squared. That can be very helpful. In other words, if I were to rearrange this a little bit, I could say that cosine squared x would be equal to cosine 2x minus sine squared x. I didn't leave myself enough room there. Let me start over there. I could say that cosine squared x is equal to cosine 2x plus sine squared x. So in other words, I'm solving for this, so I move the sine squared to the other side. Well, in and of itself, that doesn't look all that helpful. Hang on, I think I made a mistake. Hang on one second. Okay, sorry. I guess I'm a little out of it tonight after making some parent night videos all day. And anyway, I digress. If I look at this double identity for cosine 2x, I see that cosine 2x is equal to cosine squared x minus sine squared x. Well, I know that cosine squared x can be expressed as 1 minus sine squared x. And then I still have this minus sine squared x. So I can say that cosine 2x is 1 minus 2 sine squared x, or that cosine 2x minus 1 over negative 2 is sine squared x. Now I feel like I'm getting somewhere because I want to get sine squared x to not have an exponent, and look what happens there. Now, I will say that that's kind of an ugly format, so let's say that sine squared x equals, let's distribute the negative up top, so that would be 1 minus cosine 2x over 2. So sine squared x is 1 minus cosine 2x over 2. Okay, that's an important part of the double angle identity that you need to use. So either you need to memorize this identity and be able to switch it around, or you need to know that sine squared is 1 minus cosine 2x over 2. Back in the day in pre-calculus, we used to teach power reducing identities, which is really just what this is. All right, on the flip side, if I want to have cosine x, I could say that cosine squared x, so I start with my cosine 2x here equals cosine squared x minus sine squared x. And if I want to solve for cosine squared, that means I need to change the sine squared into cosine squared. So cosine 2x equals cosine squared x minus the quantity 1 minus cosine squared x, which is 2 cosine squared x minus 1 equals cosine 2x. So if I want to solve for cosine squared, that's going to be 1 plus cosine 2x over 2 equals cosine squared x. Okay? So cosine squared x is 1 plus cosine 2x over 2. So if you can remember that cosine's got the plus and sine's got the minus, those are not that hard to memorize. But what they do for us is huge. I don't know if you remember what we integrated cosecant squared, and that wasn't hard to integrate because whose derivative is cosecant squared? It's cotangent, or negative cotangent, I should say. But when I have sine squared, I have no way to integrate that because I don't have a chain rule for integration. So I have to use a power reducing or double angle identity in order to accomplish that. So if I rewrite sine squared as 1 minus cosine 2x over 2 dx, and let's factor out the 1/2 just because it makes it easier. I really don't even have to use a u substitution except for the angle. So I have to undo the 2 du from the cosine of the angle 2x. So that means I'd need a 1/2 in front of just that term. So in other words, when I integrate, the 1/2 stays out front. When I integrate the 1, I know that becomes x. When I integrate cosine, I know that's sine, but because of that 2x, it's going to be negative 1/2 sine 2x plus c. And then I could distribute the 1/2, so I'd get 1/2 x minus 1/4 sine 2x plus the cupcake. Hopefully that makes sense, and tomorrow we will do some practicing with the powers on sines and cosines. But you do need to know your double angle identity, or that cosine squared is 1 plus cosine 2x over 2, and sine squared is 1 minus cosine 2x over 2.